Colloquium series this week. We're happy to have Professor Gabriel Aeppli visiting for the workshop going on this week. So he'll be talking about the next life of silicon. Actually, Gabriel, he got his PhD in electrical engineering at MIT, and he worked on industry for a long time at IBM, Bell Labs, and NEC, I don't know if you, okay, Nippon Electric Corporation. He's co-founder and director of the London Center for Nanotechnology. He was also the Quain Professor at University College London, and currently he is the head of the Photon Science Division of the Paul Scherrer Institute. And also he's a professor of physics at ETH in Zurich and in Lausanne. He has worked on problems ranging from liquid crystals to magnetic data storage, and currently he's focused on applications on nanotechnology and photon science to biomedicine and quantum information processing. He's got received several prizes, like the Mott Prize at the Institute of Physics in London, the Oliver Buckley Prize of the APS, the American Physical Society, the Neal Medal or International Magnetism Prize of the International Union of Pure and Applied Physics. He's elected to the National Academy of Sciences of the US, to the American Academy of Arts and Sciences, and to the Royal Society in London. And he's been advisor to numerous private and public entities worldwide, is engaged in funding and evaluation and management of science and technology. So we're happy to have him here. Please.
Sao Paulo is really a wonderful place to be. I love going to places where there are no other tourists. It's really, and at the same time, obviously, it's fantastic to see all of the physics that's going on. I was out at Campinas on Monday, and I saw that Brazil is now building what looks like the world's most advanced synchrotron. Hopefully, we'll be able to do something like that in a few years' time in Switzerland as well. But it's very impressively sort of the technology and science base here in Brazil. And I've also been very impressed by all of the physics that we've been hearing at the workshop that I was also kindly invited to. So today I'm going to tell you mainly things that you already know. Actually, that are sort of part of the scientific and engineering, and indeed our general culture. I'm going to talk about the world's most ubiquitous element, beyond the iron, perhaps. And it's just basically we've managed now to build this entire society, information age society, on sand, because in sand is, of course, where we find silicon. So I'm going to try to convince you that there's life in silicon, even for science. After having done so many things with this material for the last 50 years. And I think it's very much related to this workshop also that you're running during this week. So let me just start off by acknowledging the many collaborators I've had over the years in this project, and they include a lot of my associates who were at the London Center for Nanotechnology, but also it includes people in the Netherlands, people in the south of England in Surrey, also up in Glasgow, and as far away as Beijing, and also Florida. So obviously none of this stuff I'm going to talk about would have happened without sort of the large multidisciplinary team that's represented in this slide. So, and I wouldn't be here without these people. Let me just start by reminding you about sort of the big things in solid-state physics, or a few big things in solid-state physics over the last 30 years. Of course, one very large thing which keeps coming back again in various guises are of course, the famous quantum Hall effects discovered originally in their integer version by von Klitzing about 40 years ago. And as time goes on, we found first fractional quantum Hall effects in gallium arsenide heterostructures. And then eventually, most recently, finding fractional states even in graphene, as well as not just ordinary sort of quantum Hall effects, but also spin Hall effects. So this idea of quantization of conductance is really a very profound sort of result from condensed matter physics. And this has been a topic that keeps coming back for every new material. One asks, is there some kind of a quantized conductance that we can find? So this is one big thing in condensed matter physics that we've seen over the last 40 years. It did not exist 60 years ago, and people were not even thinking about it. Other things, of course, fundamental phenomena in condensed matter physics is shown here. This is metal insulator transition. Of course, our entire semiconductor technology relies essentially on regulating metal insulator transitions at room temperature in the form of gating, let's say, silicon, where there's some dielectric on top, which is typically silicon dioxide, and converting something from an insulator into a conductor. Again, this has taken on this understanding this metal insulator transition is fundamental essentially for all of our technology, but it's also remains a fundamental question in physics, and try to understand why some things conduct and why other things don't, and how I can go between the two. This is just an example of one thing that we've worked on. There are many others where it happens also that the metal insulator transition coincides with a magnetic phase transition, basically from an insulating paramagnet to a ferromagnetic metal. So I'm not just flashing view graphs. What you see here is the conductivity. Here you see a parent compound, which also actually happens to be a silicide. Conductivity is very low here, black, near zero. It's an insulator. And then as I dope this insulator, in this case with cobalt, I induce a metallic phase, but also a magnetic phase. So this is another phenomenon that coincides with a metal insulator transition, not something you would find in silicon, but nonetheless related. There's all kinds of things that one can think about to do, not just with the diagonal conductance, sort of the conductance that you measure longitudinally, where the current is basically along the direction where you impose the voltage. There's other effects as well, particularly the quantum Hall effects I showed you before show up, of course, in the Hall effect, which is the transverse conductance sigma xy. And a lot of materials physics is done to try to understand, where these conductances lie as a function of interesting variables. For example, here, this is a magnetization. These are a whole bunch of materials which display some form of magnetism. What's rather curious is that this Hall conductance, actually, a lot of materials that we know and love actually lie very close to some kind of universal curve. This is another topic related actually to topological matter, which people are working on a lot these days, and again was really not anticipated 40 or 50 years ago. There's more things. Some of these phases in some of these phase diagrams are not conventional metals, as one might suspect, based on the Landau's Fermi liquid theory, which says that at the end of the day, electrons don't interact, and all metals then behave in the same way. I don't want to take you through this, but condensed matter physicists look at the details of electrical transport as a function of temperature, magnetic fields, and find peculiar power laws for the temperature dependence and field dependence of these basic quantities. And again, in the last 20, 30 years, we found a lot of anomalies. Of course, the thing that generates the most popular excitement in solid-state physics is shown here. So this is superconductivity as a function of time. Actually, it ends in 2010. Actually, since 2010, there's been one important development, which is that we found a fairly conventional hydride, actually, which has a TC under pressure of about 200 Kelvin. So over the last 100 years, we've seen actually, since the discovery of superconductivity enlightened by Camerlanonis and mercury, down at a few Kelvin, we've seen essentially what amounts to 2 orders of magnitude increase in the transition temperature. And alongside that, of course, as things have become increasingly practical, like with these transition metals, niobium and their derivatives, we have a technology which gives us, for example, hospital MRI scanners. But since then, actually what's interesting is hospital MRI scanners work on very old-fashioned superconductors, which were discovered, as you can see here, about 60 years ago. But since then, this quest for room temperature superconductivity has been a tremendous motivator for the field, and also, of course, been the source of a lot of sort of popular speculation about what the future might look like. So condensed matter physics, of course, then tries not just to find these high TCs, but also try to understand the mechanism. You understand the mechanism, of course, is interesting for intellectual purposes, but also for the purposes of designing new materials. And I'm just showing you here how these, some of these high temperature superconductors, copper oxide superconductors, actually live in phase diagrams which are in close proximity to other interesting states. In particular, the cuprates, the copper oxide superconductors, for which Bednorz and Müller got the Nobel Prize about 30 years ago, live in a very lively phase diagram, not far actually from insulating antiferromagnetic phase. Okay, so there's a magnetic phase and an insulating phase. This is a metallic phase. And they also live rather close to sort of a charge and spin density wave ordered phase. And a lot of what people do is try to study these phase diagrams and the behavior of materials as a function of composition, temperature, magnetic field, whatnot, to try to get a handle on the underlying mechanism of these exotic high temperature superconductors. Now, of course, I've now just presented to you a bewildering array of things, and if you're not a condensed matter physicist, you would have just thought I was just presenting you some tour of some zoo, you know, with monkey house and alligator house and elephant house, and maybe you're right, but there are a few things that people keep coming back to. The question of what is the simplest sort of model that one can use to essentially derive these properties, hopefully from some kind of first principle. So there's a quest to simplify all of this stuff. I talked about, you know, gallium arsenide, I talked about copper oxides, I talked about silicides. But the question is there some underlying model, of course, that accounts for all of this? And of course, as physicists, you know that there's an underlying model. You know, you can essentially, if you like, write down the Dirac equation for interacting, for a bunch of particles interacting with nuclei and interacting with each other through the Coulomb interaction. So that's a very complicated thing to solve. If you can't just put that on a computer and solve it. So people have been engaged in a quest for simplicity, and arguably the simplest picture of a solid is encapsulated by something called the Hubbard model. So there's really only two essential ingredients in this thing. One is that electronic waves can propagate through a solid as they can through free space. And that's accounted for by the first term in this Hamiltonian, which is just a hopping Hamiltonian. It just says that essentially particles can hop from one side to another. You can form then on a regular lattice coherent bands. You could derive a band structure where you essentially can convert these operators which are local in space to operators that are local in k-space. Momentum is a good quantum number. And so that accounts for the fact that sort of what we know about quantum mechanics in free space. And then the second term here is called the Hubbard-U term. It's simply a Coulomb interaction, which says that actually when there are a whole lot of electrons, no two electrons like to live on the same site at the same place. And so again, what our community has been trying to do now for the last 20, 30 years is try to reduce essentially all of these complex phenomena to somehow a Hamiltonian as simple as this. Of course, it is a bit more complex because I should be adding, of course, the ions here, which can move. I should be adding magnetic fields, but fundamentally, this is what the electrons do before you throw in the ions and things like external magnetic fields. And so this U term, just to put a fine point, is this just summarizes the Coulomb interaction, and it's assumed in this model to act only on individual sites simply because it's typically screened out in most real materials at larger distances. And so this has been sort of the holy grail. Now, what's happened again over the last 20 years is the realization that that Hamiltonian may be correct, but you do have to think a little bit about the lattice on which you're living. And in fact, lattices which have more than one atom per unit cell, for instance, the famous honeycomb lattice, which characterizes graphene, can have interesting free electron propagation properties as well. So we've added essentially this fact that if we start to think about more complicated unit cells, and perhaps just a square lattice or just a simple linear chain, is that there's additional physics actually coming in the first part of that Hubbard model, which is essentially telling us about free electron propagation. And of course, this this fact that you can look at non-Bravais lattices, i.e. lattices with more than one atom per unit cell, allows you actually to explore physics which has been sort of explored mainly by the high energy community. You can explore actually Dirac fermions. In other words, the fermions can have conical dispersion rather than parabolic dispersion, which is of course what you learn first when you look at the Schrödinger equation. So this essentially maps the problem of electrons propagating here map onto a Dirac equation. But this is just in the one electron part. Actually, the electron-electron interactions here give actually some non-trivial results. I'm not going to derive these for you, but they preserve these cones, but actually the cone is converted into an hourglass. So when you add that U term here, actually, and in this case, actually you have to be careful. You have a U term, but then you have to take care of the further range interactions as well, because screening is not so good. But when you add the Coulomb interactions, there's something qualitatively new that happens. And so this is one sort of interesting development which has come sort of after these discoveries that I mentioned. And the other development, of course, is that as people have been looking at these materials, these funny materials with non-Fermi liquid states or high temperature superconductivity, is these funny materials actually turn out to be rather more complicated than one thinks based on that simple Hubbard model picture that I just showed you a minute ago. In fact, the high temperature superconductors, at least some of them which have been optimized, are hardly homogeneous materials, and this just shows an X-ray scattering experiment which shows in what sense these materials are inhomogeneous. It doesn't matter. The fact is that this X-ray diffractogram is very position dependent, even though the material is a very nice superconductor and is itself looks chemically homogeneous from the point of view of X-ray diffraction. It in fact is not. So this whirlwind tour that I just gave you just gives you essentially an overview of sort of the wonderful world of condensed matter physics. where we think that we know that the key ingredients are essentially some kind of propagating electrons, and some account for the Coulomb interaction, perhaps some interactions also with ions through phonon motion. But then when you start looking at things in more detail, actually life is actually a bit more complicated than that simple Hubbard model. But interestingly enough, that Hubbard model is, although it's simple to write down, has really not been solved in more than one spatial dimension. So this sort of presents the dilemma of condensed matter physics. Lots and lots of interesting phenomena, lots and lots of theorists with lots and lots of interesting theories and phenomenologies. Some very simple starting ideas, but then a fair bit of complexity when you actually get down to detail. And so, of course, this just summarizes what I just said. Actually, at the end of the day, these Hamiltonians, including the Hubbard Hamiltonian, are actually frequently subject to debate. So this is where we are. So the question is, how can we advance? Well, one of the most successful sort of developments in physics in the last, again, 30 years has been the discovery that we can use atomic physics to rescue us. Atomic physics is, to start out with, much simpler. And interactions and atoms, of course, in vacuum at dilute limit, of course, don't interact very much with each other, but they can be actually brought to interact a lot with light, and also, of course, with external electromagnetic fields, static fields as well. And what's happened over the last 30 years is there's been the development of a toolkit to actually come at the problem of interacting sort of many-body physics, of quantum many-body physics, where you actually build the quantum many-body system from simple elements that you can understand and that you can control. And so we have this ability with optical tweezers, for example, to put atoms in particular locations. We have this famous Feshbach resonance, which allows us to tune the interactions between atoms. We have, of course, different nuclei. We heard about that this morning, which can be, depending on whether they're odd or even, can be fermions or not. There's all of these things. And then there's this ability, of course, again, using light, the generalizations of the optical tweezer principle to create all kinds of traps, which are essentially the analogs of lattices. And so we've actually gotten to a point where we can get at complexity from simplicity rather than the normal condensed matter route where we go from what looks like complexity towards simplicity. So we've inverted that. Now, this, of course, this field, I hardly need to tell you, has produced a lot of beautiful images. This is one of my favorite, which got basically Wineland the Hiroshi Nobel Prize. These are actually these are ions in the trap where essentially the quantum state has been dialed in of these ions, which are then actually imaged. And these are individual ions that have been imaged in this trap. Very pretty pictures. And the question, of course, that one can ask is why should condensed matter physicists just let the atomic physicists have all the fun and be the ones who are starting with something that they understand and then moving into sort of many-body physics? Is there not something that we can also do from our side? And here, actually, being quite lucky in the last 10, 20 years, because of this tremendous interest in quantum information processing, we have become very interested in looking for systems where we can put qubits in well-defined locations and let them interact in well-defined ways. And of course, if you want to do this in a solid, you really want to do this. Of course, one method to do this is to make devices like Josephson devices. But if you want to do this somehow in the solid state in a way that's really most analogous to what the atomic physicists are doing, is you want essentially to find a common solid about which you know everything, which you can then perturb in a completely deterministic way. Now, that actually leaves you with only one choice of material as that solid, and that is in fact silicon. And so what I'm going to tell you about is we're going to use silicon as a host, as the vacuum for the condensed matter physicist's revenge on the atomic physicist. In other words, we're going to use silicon as a vacuum in the same way that the atomic physicists use the vacuum as a vacuum to put individual atoms with well-defined properties, which they then allow to interact in deterministic ways. And so this is going to be the rest of the talk. Let me remind you of something you already know. Here's silicon. It's column 4 in the periodic table. And that's the vacuum. And we know how to make this vacuum with incredible precision. This is the solid where we can make crystals literally half a meter in diameter with very, very few defects. So it really is the closest thing we know in solid-state physics to a vacuum. And now you can ask, what is the trapped ion? Well, the trapped ion is actually pretty obvious if you look at the periodic table. The trapped ions are simply the neighbors in the periodic table. So, for instance, the column 5 elements, they have one more valence electron than silicon. So it turns out that if I deposit one of these atoms in silicon, I substitute, let's say, phosphorus for a silicon atom, then what I get is essentially it's nicely bonded covalently to its neighbors. There's this spare electron here, which comes because the valence is larger by 1, which has, of course, a spare charge E and a spare spin a half. And so that's my atom in its trap. And it's a remarkable fact that to understand that spare electron, actually, all you really need to know about is a hydrogen atom. And in fact, you'll remember here the Hamiltonian for the hydrogen atom. It's just the kinetic energy term. And the Coulomb energy, which is the attraction between the electron and the nucleus. And actually, to modify that in a way that's appropriate for silicon as a vacuum, all you really need to do is replace this dielectric constant, change that dielectric constant from 1 to 11, which accounts for the screening in the silicon. And you put in here the effective mass of the electron, which is gotten from the conduction band. So the electrons are actually quite light here. And so you've just got a rescaled hydrogen Hamiltonian, and then you can write down, of course, the classic formulas. There's a Bohr radius and a binding energy. And you can see here that the Bohr radius scales like the dielectric constant divided by the effective mass. And so in the case of hydrogen, that is half an angstrom. But of course, if my dielectric constant is an order of magnitude bigger, my effective mass is a third, then that atom blows up, okay? Because the atom is more weakly bound. And as you know, also lighter particles travel further than heavier particles. And so what happens is I have a very big hydrogen atom. Not half an angstrom, but 1.8 nanometers in radius. But at the same time, of course, it's more weakly bound. The binding energy scales like the effective mass divided by the electric constant squared. And so my Rydberg, which is tens of eV, now is 70 millivolts. So basically, the physics just goes through in the same way as for ordinary vacuum. There are, of course, corrections which you'll see which are due to the fact that this vacuum is not spherically symmetric. But that's a detail I'll leave for the specialists to discuss. Just to give you an idea of what we're talking about. So we have basically silicon is an atom trap for neighboring atoms in the periodic table. And you get these giant atoms. And this is how big just the 1s orbital is for phosphorus and silicon or anything in that column. So Now, how do we know that this is real? And of course, this kind of thinking, existed, is very old. But of course, at that time, one had no way to directly check that. Fortunately, in the intervening period, people discovered scanning tunneling microscopy. I'm going to show you here that we can find some very big atoms in a doped silicon wafer. This is a doped 100 wafer. This is an STM image of that wafer with a fairly high but not too high density of bismuth atoms, so enough that we can pick up a few when we do a scanning tunneling microscopy. And what you see here is just essentially a topograph. Now with STM, of course, in addition to topography, you can also do density of states measurements. In particular, you could do, and that those density of states you just measure by parking the tip at each point on the surface and then measuring an IV characteristic, a current voltage characteristic. And the derivative of that current voltage characteristic gives you a density of states. And that the IDV map is actually perfectly lined up with the topographic map. And what's interesting here is this topograph just shows nice ordinary steps. But when I go to, let's say, minus 1.3 volts in the valence band, I actually see this rather bright object, which has no topographic signature. And what's even more interesting is that if I change the voltage slightly, I see a black object. In other words, I see a suppression of the density of states. Here I see an enhancement of the density of states. So what I see here is essentially a resonance, a scattering resonance, something which is scattering essentially the valence electrons that I see with STM that's below the surface. So it's just some weird object which contributes nothing to the topography, but which simply scatters electrons at the surface. And that object actually, if you measure the radius of that, actually precisely, the radius of that object precisely matches this Bohr radius that I calculated a few minutes ago on the back of the envelope. So that's how we know these things exist. Now, another thing that we've known for a very long time, that's the charge, is that these atoms carry spin. And that's known since the 50s when people did electron paramagnetic resonance. I'm going to take you through that simply because it's going to be important for what I'll tell you about in the rest of the talk. It sort of reviews some important concepts. So basically, what we're interested in is this spin. That spin, of course, has been there for a long time. We've measured it with resonance. But what we're particularly interested in is if that spin is really is really free. It really has a very long decoherence time in the sense that I can create, as I can in atomic physics, coherent superpositions of up and down spin associated with that atom that I've trapped. Because I'm going to focus really mainly on spin dephasing. And this is just a brief review of how we think about dephasing in quantum mechanics. So if you have a two-level system, such as, let's say, spin a half in an external magnetic field, I can represent, of course, the entire Hilbert space as a block sphere. North pole is one of the two eigenstates. South pole is the other eigenstate. And then, of course, in between, I have all other possible superpositions of up and down states. And the decoherence time that's most interesting is really related to the lifetime of one of these coherent superpositions of the two basis functions, let's say a state that lives on the equator. And so the extent to which I can dial in a coherent quantum superposition is the extent to which I can control deterministically the state of the atom in this trap. And of course, there's a very famous experiment that one does to measure these decoherences, and it's called the Hahn-Echo experiment. And the way it works is shown in this slide, this animation, which was originally made by a postdoc of mine, Gavin Morley. What you do is, of course, the system likes to start out, let's say, at the South Pole, and then you impose a pi over, the North Pole in this case, a pi over 2 pulse to move it to the equator. Then you have a coherent superposition of up and down. Then you apply what's called a refocusing pulse. And then if you wait an exact time which is equal to the distance between the pi over 2 and pi pulses, you get what's known as a spin echo. So you can then vary this time here, plot up that echo curve, and from the decay of the echo gives you directly the decoherence time. In other words, how good is this as a controllable quantum mechanical element? And here are just some dephasing curves that we collected, Hahn echoes that we collected for, as it happens in this case, bismuth in silicon and phosphorus in silicon. What I really want to draw your attention to is, of course, first there is a decay, but the decay occurs over at 10 Kelvin. 10 Kelvin is a very, very trivial temperature to reach, and it's not a heroic temperature that requires a dilution refrigerator. You see here that these time scales, these decoherence times, are of order milliseconds. And that really means that you can actually hold quantum information in this atom trap for a time that's very substantially longer than the cycle time, for example, for your DRAM in your computer. So in essence, you've already got something here. If you wanted quantum memory at 10 Kelvin, you could address each phosphorus atom individually. You would actually be doing pretty well if you also had processors to match. So this is remarkable. So I have this solid, and I have these atoms which are covalently bonded to their neighbors, yet at the end of the day have this hydrogen-like atom with a spin, which just electron spin, which essentially lives forever, compared to any other time scale that you can think of. And of course, you can not only look at this, you can show, using, for instance, Rabi oscillations. This proves, of course, that you have a Bloch sphere at all. Rabi oscillations just show you that a pi over 2 pulse does the same thing to the system as a pi over 2 plus 2 pi n, where n is an integer. And so what this means is I can set any quantum state that I like on the sphere by appropriately choosing microwave pulses. Okay, so basically we have control of decoherence of deep impurity spins in silicon. So if this atom, this big atom, but very long t, 2 times of the spin, and we have this ability to control that state. So that's very promising. That's only one thing that the atomic physicists can do. Of course, they can manipulate the orbitals as well, and the orbitals are interesting because, of course, orbitals can, what the orbital state is of the atom can determine, for example, what the overlap is with neighboring atoms. And this is particularly interesting for hydrogen, because in hydrogen, as you know, the size, basically the size of the nth Rydberg state scales as the principal quantum number squared, scales as n squared. And so I have this giant atom, 1s atom to begin with, but if I could coherently excite to higher Rydberg states, I would have an even more giant atom, and particularly if I had other atoms nearby, I could imagine situations where there would be no overlap, let's say in the 1s state, but very substantial overlap in the 2p state. The question is, can I coherently drive that transition to produce coherent superpositions of different orbital states? And here, this is where, if you didn't listen to the spin discussion, you won't understand what I'm talking about now. But we're going to essentially do the same experiment optically with orbitals that we did with microwaves in the case of spin. Just to show you, these Rydberg states have been around for a very long time. And this is actually an old Fissor FB from 1981. And what was noted at the time was that as this is the concentration of these phosphorus atoms, and you see that for low concentrations you get very sharp Rydberg states. And as you go to higher concentrations, you see that you lose the higher lying ones first before you lose the lower ones. And of course, the reason for that is clear. I just explained it to you. I just said that the higher lying Rydberg states correspond to bigger wave functions than the low lying ones. And this is essentially what you see here. And in fact, the measure, the diameter of these states, the best measure we had was just based on such infrared absorption measurements. Okay, but what we're interested in is doing non-trivial quantum control, sort of quantum mechanics, sort of physics from the 21st century now, not from the 20th century. And it's interesting that these experiments trying to do quantum control had actually not succeeded in the last century because we didn't really know how to use certain tools that we have now. And what we have as a tool now is lasers which actually work in the terahertz domain. We've all heard, of course, about lasers, optical lasers, which, and these have been around, again, for 50 years. But lasers in this interesting terahertz regime, sort of tens of millivolt regime, which corresponds to the binding energy of electrons to impurities in semiconductors, those did not exist. And we had to actually develop free electron lasers, essentially to give us essentially coherent pulses on demand to do exactly the same experiments that we were able to do with microwaves for the spins. Now, this free electron laser that we're using here happens to be in the Netherlands. It's now located at Nijmegen. It produces pulses, and what's important is these are transform-limited pulses of radiation in the wavelength range 5 to 250 microns. That's exactly this terahertz domain that I was referring to before. And the pulses can be dialed in with lengths basically continuously between 0.5 and 15 picoseconds. So we can create essentially arbitrary length coherent pulses in this wavelength domain to essentially now do optically what people had done with microwaves for spins. And so this is what the machine, this particular machine looks like. It fills a room roughly this size. That's what the experiments look like. They look like any other optical experiments, except, of course, that we have vacuum chambers to deal with the fact that the atmosphere absorbs, has a lot of absorbers in the terahertz regime. And now we're getting back to the physics here. So now all we have to do is label the Bloch sphere. We're going to relabel the Bloch sphere. So what we're going to try to do is see if we can create coherent superpositions of these excited atomic states. And let's say I want to create wacky wave functions, which are somewhere between a 1s and 2p-like wave function. So here's my 2p, sort of these two pancakes. Here's my little sphere. And then let's say I want to go to the Bloch sphere. I get all these funny shapes here. And so, but I have a Bloch sphere, as I did before. So all I need to do is just, again, pump the material, let's say, with a pi/2 pulse, get it to the equator, put my rephasing pulse on, and look for the echo. And now we're doing this optically. This is the instrument. I won't take you through it since it's a theory center. But what's important here conceptually is what we're doing is we're doing an experiment here with 4 different beams of light, okay, 3 of which are copies, coherent copies of each other. And what I do is I actually I'm showing you a pump, and then this is a rephasing. This is a pi/2 pulse. I have a rephasing pulse, which is a pi pulse, and then I have an echo, which comes out of the sample just by itself after these pulses have come and gone. Why are these things so noisy? Well, actually, how I'm observing these is coherently. I have this 4th beam, which is another copy of the incident pi/2 beam. I'm interfering that copy of that beam with each of these beams so that I can see the arrival times of each individual pulse. And so these actually figures here are not just noise. Actually, I'll show you later if I have time that these are actually, these themselves are coherent oscillations, which of course I can only get if I have a nice coherent source. And so I've got my pump, my rephasing, and then my echo, and you can see immediately, you can read off immediately that the that the time between the pump and the rephasing is precisely equal to the time between the echo and the actual and the rephasing pulse. I can rectify these pulses because I said these are actually interferograms, and of course interferograms have a phase and an amplitude at each point. I can rectify that and look at the amplitudes, and now I get something which looks very much like electron paramagnetic resonance. But what's really remarkable here is that I have now seen in a solid, for the first time, an orbital echo coming from a superposition of two wave functions, one of which, well, both of which are very, very large. So this is now looking at these electronic states. The fact that I can see an echo at all means that they're coherent on time scales of 100 picoseconds or so, with over a spatial extent, which contains of order 1 million silicon atoms. So that tells you how clean the silicon is. That's a remarkable sort of fact of life. So the conclusion of this is that I have lifetimes, in fact, near 200 picoseconds for these 10 terahertz oscillations. So we're able to coherently control these orbitals. And so the Q, if you like to speak of that language, is something like 2000. And this has really interesting implications. This now means that we can do atom trap physics in silicon. We can control the atoms. We can control their wave functions with light. And it's also really what, we've heard a lot about spintronics, but actually we can also do orbitronics now. Now, what the atomic physicists, of course, can do better, if you look at the figures of merit for hydrogen, they are better than what we have. But of course, what we can do is we can actually we can read these states out electrically, and we can read these states out in devices. And in fact, I'm just going to breeze through one device, one type of device that we built. This is basically a MOSFET with some phosphorus in the channel. Looks like something like that. Dragana, I'm sure, could recognize that from her past. And what we actually have been able to show is that we can see electrically in this MOSFET these Rydberg states. Actually, they're very, very sharp. You can see a beautiful 2p naught, 2p plus or minus. The reason, of course, the 2p orbitals are split is because it's a cubic vacuum, not a spherical vacuum. It's actually a diamond lattice vacuum. You see, this is actually measured electrically, and one can actually switch by changing the gate. One can actually change the visibility of these excitations. So if the gate is essentially off, you can have the atoms undergoing whatever optical manipulation you're doing, and then turn the gate on, and then read out these Rydberg states. That's what my postdoc built. But let me just get into some detail about what this might have to do with quantum mechanics. And actually how actually this combination of this unique ability now to do atomic physics in a solid state system allows you to do essentially trivially, just with a voltmeter and some silicon device that you get on eBay, you could do one of the classic experiments of atomic physics. So that's the Ramsey fringe experiment. And so let me remind you now, again, if now you just need to know the Bloch sphere again. If you think about the Bloch sphere, the Ramsey fringe experiment works as follows. Of course, I can, if I have a pi over 2 pulse, of course, a pi over 2 pulse can be divided into, let's say, 2 pi over 4 pulses. And so I can build up, for instance, a state at the equator with essentially first 1 pi over 4 pulse, and then a second pi over 4 pulse. So I can split the pi over 2 pulse into 2. And then I can do various things. I can look for echoes or whatnot after I've created that. Now, if the 2 pi over 4 pulses are in phase, of course, I make it to the equator. If they're out of phase, I'm back down at the South Pole. So that's the end of the story. And now I'm going to show you that we can actually detect that simply electrically. So all I have is my free electron laser, and I've created essentially 2 identical pulses, 2 identical pi over 4 pulses, and I'm going to show you essentially the Ramsey interferogram. The first thing, of course, that you have to make sure of is that the incident beam is coherent, that these 2 pi/4 pulses are really the same. And this just shows an interferometric determination with an ordinary detector showing beautiful fringes corresponding, of course, to the frequency of the radiation. And this just shows the autocorrelation time that one picks up from this envelope function, which tells you the pulse length. So I have a coherent pulse, and I can make coherent copies of the pulses. And so now I simply now measure the electrical resistance of my channel containing the phosphorus atoms. I'm just measuring electrical resistance here. I'm just measuring essentially what I'm doing here is just measuring a curve for fixed voltage. And what I'm seeing here is this rather extraordinary thing. I'm seeing that there's this huge amount of noise, and then it decreases as time goes on. So when I put these pulses on, as I change the delay between the 2 pi/4 pulses, which make up the pi/2 pulses, actually, if I blow up what looks like noise here, I actually see oscillations. Okay? And so what I'm seeing here are exactly and rigorously the Ramsey fringes that you predict from that the atomic physicists, of course, have long known about. But all we're doing here is doing an electrical measurement, and all I'm varying here is I'm just measuring these fringes as a function of the delay between the 2 pi/4 pulses. So this is again emphasizing now we have something that goes beyond what atomic physics can do. We can do electrical measurements on devices and see non-trivial quantum effects. I'm not going to, we can talk about how it works because I don't want to spend too much time, but it has to do, of course, with the fact that the ionization of an electron in the 2p state is, of course, more favored than the ionization of electron in the 1s state, and I'm actually seeing the oscillation in that ionization. So that's my detection mechanism, but very, very simple and literally can be written down in the back of a small envelope. Now, actually one can do, having now shown this, one can do all kinds of more elaborate experiments. You can look, of course, not just at block spheres. You can look at block hyperspheres. Well, how do you get a block hypersphere? Well, if you have a high angular momentum state, not the 1s state, of course, you can split it in an external magnetic field. If you split it in an external magnetic field, now I have a quantum system where there are essentially 3 eigens spanned by 3, a bigger Hilbert space now spanned, it's a 3 by 3 eigenstates. And I can actually look for interference effects essentially between the occupancies of all 3 of these different eigenstates. And one can set, of course, the orbitals depending on how you, depending on the pulse sequence that you impose. You can, for instance, start with a 1s orbital, go to a 2p0 orbital, but you can also go to, again, strange superpositions which have directionality. Okay. So this is interesting because what it means is that if I were interested in setting up a model solid state system where I suddenly had directional bonds, I could simulate that. So I can essentially impose directionality on bonds in a solid, essentially just by dialing in appropriate radiation. Now, this is actually showing just how the Zeeman effects work. Essentially here, I just start off with this simple eigenstate, which then splits into 2. And so here, as I say, I have a block hypersphere, no longer a block sphere. But don't worry, we can do all the algebra for that. We can make all kinds of pictures of the states that we can reach once we have a magnetic field there. And we see new interference fringes beyond the ones that we saw before. In particular, before what we saw were interference fringes which are centered on a 0 time delay between, let's say, 2 pi/4 pulses. Now, if I impose a field, I still see essentially interference fringes just centered on 0 time delay. And of course, the frequency, if you analyze the frequency for this that's present in this noise, you get this Fourier transform here, and you get, of course, a photon energy, which corresponds basically to the level that you're addressing, in this case, a 1s to 2p state again. If I put a field on, I get these side lobes. Of course, the side lobes come because of the interference between the states in the formerly degenerate orbital. Now these orbitals are no longer degenerate, and I get what amounts to a two-slit interference pattern. But this two-slit interference pattern I observe in time, and I can Fourier transform that into frequency to get the splitting for my two levels. Okay? So all of this physics is just done literally with an ohmmeter now in silicon. Okay. So I've shown you all kinds of things about optical control. Let me now just briefly tell you about electrical control. And here I need to digress, and this is going to hopefully end the talk, I guess another 9 minutes or so. To sort of see whether orbitals can be controlled electrically or not, you have to work, at least in the first instance, near a surface where you can actually apply electric fields and see with STM what you're doing. And so as a model system, we looked at the surface analog, essentially, of phosphorus in silicon. And this is going to require a little bit of imagination, but typically, of course, silicon 100, silicon, when you cut it, is no longer happy. You've broken inversion symmetry, and there are a lot of unhappy electrons. And these are called dangling bonds. And then these dangling bonds have a great affinity to be attached to hydrogen atoms, which you might insert into your vacuum system. So typically, what you do with a silicon 100 sample is you so-called passivate the dangling bonds using hydrogen, which are these little atoms on the top of this figure. Now, let's just look at two of these hydrogen atoms. So one thing, or one of these hydrogen atoms. So if, of course, for some reason you were able to remove one of these hydrogen atoms, you might actually find that you then had a spare electron there. And in fact, that vacancy, that hydrogen vacancy, is then very much analogous to the phosphorus atom with a spare electron in the bulk of silicon. And so what one can do is do model experiments on the surface of silicon, simply using this expedient of removing individual individual hydrogen atoms to reveal essentially these dangling bonds. So these electrons at the dangling bonds. The way we remove them is with an STM tip. And so if you go through with an STM tip, then you can remove atoms, or pairs of atoms sometimes. And then, in fact, one can do lithography with this removal technique. So you can make all kinds of funny patterns by removing selectively with a STM tip these hydrogens. And now we're just going to talk about the physics that one can do. So, of course, one dangling bond is not terribly exciting. The talk is about many-body physics, so maybe the first thing to do is to look at two. And so what we did is you started with one dangling bond, and then what we decide to do is we desorb a second one using a voltage ramp next to it, and then we'll look at what the STM images look like. And so the way we do that is just illustrated in this animation. So I just keep hitting this region of the sample with ever larger voltages. And eventually, if I hit with a large enough voltage, I get a bigger object here. I get an object essentially with which is 0.77 nanometers, sort of almost a nanometer across here, where essentially I have two electrons now, which wander around in this little quantum well. And so I can control that. And what's very interesting is I can actually, let me just see if this, oops, it's not, let me just see if I can get this tip. Animation isn't working. Okay, the animation, I can't get the... Oh, here it is. What I'm doing here is I'm now changing, in this case, the tip sample distance. And what's very interesting that's going on here is as I change that tip sample distance, of course, I'm changing the electric field at the sample. And as I change that electric field, I'm actually finding that the image changes. And so what I'm doing here somehow is with my STM tip is I'm changing the nature of the orbital. So I'm actually switching the orbitals that live in this primer object. Okay, so sometimes you see two things at this side, and sometimes this is two, and at other times you see three things with a very bright object in the middle. So one might actually ask, well, what is this bright object actually in the middle? What am I actually doing here? Well, all you need to do to understand this is to remember some simple physics. If you think from your freshman quantum mechanics course, you have your potential well, a double well. Then, of course, for low energies, of course, the electrons will sit, mainly in one or the other of the two wells. But as I go up, I of course find excited states here, which would actually preferentially sit in the middle. So what I have here is this tiny quantum box that I fabricated, where I can actually tune the orbital state, essentially simply by either tuning the tip sample voltage, or essentially by shifting the Fermi edge relative to these levels. And the way I'm shifting it is shown in the upper part of the slide. Let me just see here. As I shift it, of course, I'm shifting the occupied states closer or further from the Fermi edge. And then depending, of course, on where I am here, I can either expose two blobs or a blob which contains mainly something in the middle with two side lobes. So I have electrical control here over the orbitals. Now, this scheme actually can be generalized to look at chains of atoms. So I can actually make chains of dangling bonds, model atoms, using the STM again. And here I'm just showing you a case just again with you can see that there are 1, 2, 3, 4, 5 atoms. And for instance, what point at a voltage, a bias voltage of 1.4, okay, this is going into the conduction band. What I'm seeing here is no longer homogeneous. I see small density, high density, small density, high density. So it breaks the periodicity that I had when I'm just doing topography at minus 1.4 volts. On the other hand, actually, if I change the bias voltage, then I occupy a different state. I occupy a state essentially which is only between between these atoms. So I have essentially a model quantum well system that I can build on the surface of silicon. And I can not only build it, but I can control it with STM and measure its properties. And here is just some calculations that we did to account for these densities. Okay, so these are, I could do it with 6. I could do all kinds of things. I can even make squares. And actually, by changing the tip sample voltage here, I can also get different wave functions to pop up. So for instance, here, the wave functions are centered essentially on the vertices of the square. If I change the voltage, I get a flower. So I have essentially control over orbitals in essentially the world's most common material at the surface. So let me conclude here. So we've actually been able to construct quantum states here. Now in silicon, you've of course all seen quantum states constructed by Don Eigler. Basically in metal atoms, these are essentially standing waves. You've seen also in atomic physics, and this is of course why I showed this picture at the beginning, atomic physicists have nice controlled ionic states in atom traps. But now we have our atom trap where we can do just as well as these guys. So I think we are starting to, as I say, improve our game as condensed matter physicists. Okay, so I've shown quantum engineering using STM at the surface and using optics in bulk silicon, phosphorus doped silicon. And so the logical next step here is to ask can we really do all of this kind of physics that we're doing at the surface and this kind of optics, can we do it with deterministically placed atoms in silicon? And I'm just going to now tell you how that is done and then conclude. So I've shown you how you work with a lithography. I've shown you how you've created essentially deterministically these dangling bonds in dangling bond patterns on top of silicon 100. And the next step is actually what will lead to implementing what I just asked. In particular, what you could do at the next step is you could actually introduce phosphine into the vacuum chamber. And the phosphine actually does not, of course, again, looks for unhappy electrons. And these are the dangling bond states. So what happens is a phosphorus goes to these places where we have missing hydrogen atoms. And so in essence, what I have is a positive pattern, essentially a lithographic process now, for putting phosphorus in well-defined location. Of course, after I've introduced the phosphine, the phosphorus actually binds very strongly into the surface. It actually substitutes for a silicon atom. At that point, I can actually anneal the whole business, get rid of all of the hydrogens, and deposit on top, using molecular beam epitaxy, I can encapsulate these nanostructures with more silicon on top. And I can, of course, bury devices and contacts and all kinds of things. So down here, I can actually create little structures, permanent structures, engineered permanent structures for doing interesting quantum mechanics. Actually, we can make not just one-dimensional or two-dimensional structures, we can even make three-dimensional structures. Actually, this is just an experiment that we did to show we can do that, and not only could we actually insert these little atomic strips into the bulk of silicon, we could also image them later using near-field microwave microscopy. Okay, so I've shown you a lot of stuff for silicon, so let's go back. What does this all have to do with the Hubbard model? So we've started, of course, now that I have this ability to build these structures, we could actually go back and think, well, can we build a Hubbard model on a particular lattice? And so if we can the phosphorus atoms, for example, in well-defined locations, then literally we can make a Hubbard model that we can then control, let's say, hopefully optically, and also measure electrically. We can, of course, vary the lattice constants at will and look at phase diagrams. Essentially do all of the very pretty physics in the same way that the atomic physicists are looking at their version of the Hubbard model. We haven't actually implemented that yet for the ordered Hubbard model, but we have certainly started doing experiments where we've looked at disordered two-dimensional physics, the disordered two-dimensional Hubbard model, and in particular what we've already done and we've published is actually a look at the disordered 2D system and at a density which is much higher than what has been achieved with silicon MOSFETs. So this just shows a table. I'm not going to go through the details, but the point is that we can actually go into a regime where our carrier density per square centimeter is 2.8 times 10 to the 14th rather than 0.07, which was sort of the largest that was achieved in the MOSFETs. But we're also here dealing with a phosphorus array, which really has a well-defined U at each site. We know where the U's are coming from. And what, in essence, what happens for this particular system is we have all of the usual transport data and everything else for the situation where T over U is very close to unity. And I'm not going to talk about all this data, but what's remarkable is that the theory, the known theory for essentially the disordered, basically two-dimensional Fermi liquid actually works perfectly. when T over U is of order 1. Now, so that's silicon as an atom trap. Of course, what's coming next is, as I said, we're going to do deterministic things. And also, one thing to realize is, of course, is that these systems in some ways map onto the Hubbard model, but there's actually a multi-orbital aspect to this, because the higher-lying orbitals are so much bigger than the low-lying orbitals because of this n squared, which is the scaling of the size of the orbitals with the principal quantum number. And this just shows you how these orbitals grow in size. Also, of course, you can dope these materials not just with donors, which have one more electron. You can, of course, also dope with acceptors, essentially, which have a hole rather than an electron. Now, that's rather hard to do in atomic physics. And of course, these have even stranger looking wave functions. And of course, the physics of arrays of these it may well depend actually on what goes on for these higher lying Rydberg states with all kinds of funny shapes, which, as again, I remind you, can actually be optically steered. So the picture, of course, that one has is not just the humble Hubbard model, but actually you have, let's say, all these 1s orbitals, which have their physics, but then on top of them, of course, you have these gigantic orbitals with very funny shapes, which you can actually control optically. And in fact, we've started doing some of that physics. We've actually done some photoconductivity measurements where we look at these Rydberg states where we change the gate voltage. In other words, we put them in contact with an electron reservoir, and we're finding actually very funny-looking line shapes as we go through the metal insulator transition, in that case, by adding electrons through a gate. I don't want to go into the detail of that, but the point is that the physics that's encapsulated in this cartoon is well alive and progressing. Another thing, of course, that has really motivated us from the beginning of this project is this possibility, of course, with orbital control, optical control of the orbitals, that you can control magnetism. And it's quite simple to see how that works, and I've just constructed this video to show that. Let's say I have two impurities which are relatively deep, bismuth impurities, let's say, separated by a phosphorus impurity. And so I have, of course, my long-lived spin states associated with each of the bismuth. And of course, if the phosphorus is sitting in the 1s state, there's not much overlap with these neighbors. Of course, if I come along and coherently excite the phosphorus with terahertz pulse, then the wave function of that phosphorus expands actually to have substantial overlap with, let's say, the 2p wave functions of the bismuth atoms. Okay, if this thing is, of course, clocked, because it's a coherent excitation, I can actually have a timed exchange interaction between the bismuth spins. So after, of course, the pulse is gone, and I've de-excited coherently, I can actually be left with, let's say, the spins in opposite directions. So I have actually a possibility of doing essentially a timed exchange interaction if I could figure out how to put, let's say, a heterogeneous device like this into a wafer of silicon. So that involves, of course, some work on the chemistry, the phosphorus chemistry. We understand the bismuth chemistry a little bit less. But this is essentially a quantum gate, or if you wish, a programmable quantum magnet, optically programmable quantum magnet, which we hope to implement in silicon. Okay, so let me summarize. I think I've talked too long. Impurities in silicon are actually starting to become as controllable as atoms in vacuum. And we, of course, don't have quite as big or elaborate a toolbox yet as the atomic physics community has. But our toolbox is somewhat different. It includes STM writing multiple impurities. We've worked with the phosphorus, with hydrogen. We have actually also worked with arsenic, which has some interesting aspects. We can work on these passivated surfaces in silicon in processes which seem to be compatible with CMOS. And of course, a lot of the new physics that we've been able to do has been enabled by the sort of the revolution in being able to handle terahertz radiation, which is really only starting to gather steam in this century. We believe there's going to be a lot of great new quantum many-body physics to do, and hopefully also some technology for the people who fund us. Thank you very much.
Thank you very much. We have time for a couple of questions.
So Gabe, this really looks very exciting, but can you give us a feeling for a time frame where many-body physics in the sense of lattices will be accessible to a broader set of people? How many people are getting involved in this type of work? And what's the roughly the time frame for starting to probe the Hubbard models and stuff?
Well, in many ways, working on silicon has been deeply unfashionable in physics because I think it was. So there's a few groups which have the technology. There's of course the New South Wales group, which is much bigger than ours, which is much further, and with actual single atom device chains and so on. And they're actually in a position to do the experiments effectively now. We have, but in the States, there's of course, as you know, there's groups at Sandia, and there's a group that just started at. And so I think there's a growing momentum worldwide to kinds of experiments. So it's very much, I think, analogous to sort of the beginning of this whole quantum many-body physics with atomic physics about 20 years ago when there was one or two groups. But what we're seeing, I think, is a growing interest. So I think that over the next, getting into the interesting regime for the Hubbard, for the for the ordered case, I don't think people are really there yet, but could be there very, very quickly if they put their mind to it the next year or two. And so and then the question is, what happens with other atoms, with arsenic, with bismuth, then doing things with holes rather than with electrons. So it's basically. So I would say over the next 5-10 years, you're going to see a lot of things happening here.
I have a question about the orbital degrees of freedom.
Mm-hmm.
When you talk about the SP and so on, so, okay, in the real atom, you have the azimuthal degree of freedom.
Yes.
For really getting SP. Now you are patterning something in 2D.
Right.
You were drawing these harmonic oscillators as an image, but how much is this really true?
Oh, that is not, that's phenomenology.
Yeah.
So those pictures match up the data with that phenomenology.
Uh-huh.
And so basically what you have, and you're talking about the STM.
Yes. Uh-huh.
Distances that we actually see, we don't have a first principles. Inevitably also actually evolved, there are many-body effects there because these electrons are not alone. I have a whole set of dangling bonds and the electrons are not alone, and then they're coupled to a bath which comes from the band bending. So there's a tunneling term, of course, also to the surface states, the other surface states from the band bending. So it's an interesting many-body physics problem, but just at first sight, you can just see you have a quantum well which you've created deterministically, and it looks, control it. You can control these wave functions, and you see them move around, and you're obviously not moving the atoms. The only thing that's moving is the electrons as you change the voltage.
Yeah, it would be more like P-like.
Yeah.
More than really orbital.
Of course, as you saw with a square, it's D-like. You create a D. You create this. Magic. It's really amazing. You generate essentially a D-wave type symmetry. So that's where the electrons live, and that's not a artist's conception. That's just what you see when you change the voltage.
All right, maybe one last question, and then we'll refreshments, and we can.
Okay, so thinking about quantum simulators, one of the special things is in atomic physics is that they are extremely clean.
Right.
So how close can you get to the same level of cleanliness if you put your impurities in silicon when your silicon itself is not vacuum, right?
Well, the silicon is vacuum. That's the remarkable thing. I mean, that's actually one of the extraordinary achievements, essentially, of chemical engineering, which is that these remarkably high decoherence times. So we measure these, when you have decoherence times that long, there are no impurities there. And silicon also, you can measure, you measure X-ray diffraction. Essentially, you get perfect, you get dynamical diffraction effects, which can only happen if you have perfect lattices. So silicon is the only thing with which you can do this. The more relevant question is, of course, that after you have built the structures, then things do get messier. And in fact, we've been making a lot of progress on improving essentially the overgrowth process, because the wafers that you get, which are zone refined in a factory, which you buy on eBay, they're very clean. But then you do all this processing, and once you do the processing, then there are problems. And the question is how important those are. Of course, you realize in atomic physics there are also issues, because do you really get a perfect corrugated lattice? You always have some edge effects, and there's always one laser in the problem, one mirror that has some dust on it. So I think that in the long run we will probably be at that level, because even with atomic physics there is some disorder, and so we're very far from achieving the cleanliness, of course, that exists now. But each year actually we've been making progress on essentially controlling. For example, one key step. I mean, this is boring material science, but one key thing is that anneal that you do after you've placed the phosphorus atoms, and you have to optimize that in such a way so that you get rid of the hydrogen, you clean the surface of the silica, but that the phosphorus doesn't move. And so there are tricks now that we're developing to do that. But there's a lot of know-how that still needs to be refined to get to the perfect realization we hope for.
All right. Thank you very much. And there should be refreshments upstairs, so feel free also to ask more questions.